Okay, so just to remind you where we are. Okay, for your programming test 1 from Monday, I really will try my best to really return the result and feedback back to you by next Friday. I know that it's going to be some important day for some of you to make some decision. I hope everybody will stay, but no matter what, I'll give you the feedback and the result. Hopefully by the end of Thursday, I already contacted the TA to coordinate them about the grading. So we want to make sure we grade it properly. You will get a chance to really apply for reappraisal if you want to get it regraded. There will be a mechanism for you to do that. But anyway, just bear with me. By the end of next Thursday, I'll reach out to you and then about the mark. And just to remind you, so far you got 2 makeup lectures. Remember, we got written test 1 and programming test 1. Let me show you again. Just make sure you don't miss that important information. If you go to the lecture site, as usual, you will see that makeup lecture number 1 is what I announced earlier. So make sure you study that. And there was this makeup lecture number 2 for your programming test 1. That one there is actually talking about something very interesting. So one thing is about binary search algorithm implemented recursively. That's number 1. And I remember one of you guys actually asked me before, how do we argue about the asymptotic running time for recursive algorithm? Starting from this particular lecture, you're going to learn about it. I'll give you some very quick look ahead about what you're going to learn. Hopefully that will give you some motivation. Right? Of course, you're going to follow through the lecture, but I'd like to show you around the end. You will see how we can derive mathematically the big O for recursive algorithm. So this is something that you will have to do. Okay? It's very different from how you argue for algorithm containing just iterative loops. But for recursive algorithm, you have to do something called unfolding. So this really requires very careful steps to really apply the unfolding. So in the video, I try to walk you through very thoroughly about the process. Overall, we're going to learn about 3 recursive algorithms, for which we're going to learn about how to unfold their mathematical function for the running time and derive the asymptotic upper bound. Binary search will be the easiest one, just to get you started. And then a little bit later, I'm going to give you also the resources for merge sort and quick sort. So these are also the very typical recursive algorithm you have to know. In that case, we'll see how we can argue the running time using the same unfolding procedure. So one thing at a time. Please do get started with the makeup lecture. Whenever you got any trouble understanding any one of them, drop by my office hour. We'll make an appointment. Right? You know the rule. Just reach out to me. All right, so that's about the makeup lecture you really have to pay attention to. And then let's take a look at the calendar, right? Everything will just go on schedule. It's not going to change. Okay, so we are exactly here on the 8th. We're going to do some lecture today. And then I'll definitely return back to you the result before the 16th, okay? And then around the class on Wednesday, maybe shortly after that, I'm going to give you assignment number 3. Assignment number 3 and assignment number 4. Well, specifically assignment number 3. It's going to suggest the format for your upcoming programming test 2, which is going to be very similar to programming test 1. I'll talk a little bit more about it. If I can somehow touch some Java code about implementing tree, I can maybe mention that. But you can expect to receive assignment number 3 and you get enough time to work on that. I'll give you solution and also some other discussion as usual. The upcoming assessment is not this week anymore, also not next week, but it will be on the 20th. So whatever I can finish by the end of next Monday is going to be covered in your written test number 2, right? So you do have about a week to really review the stuff and get ready, okay? Okay, that's about where we are. Just make sure you're okay. So guys, any question, any concern you would like to mention to me? Everybody's good? Okay. Oh, you do have a question? Yes, please. Oh, good. The question was what exactly will be the coverage for written test 2? So it's not going to be cumulative. Whatever that was already covered in written test 1 is not going to be covered anymore. If there's any overlap I would like to cover, I'll make it very explicit on the guide. But in general, it's not going to be a cumulative. Okay. So guys, I think I will try to reach out to you maybe after Monday's class next week to tell you exactly what you should really study for. But what's going to be at least that's going to be covered. You really want to make sure you follow through the lecture for makeup lecture 1, right? That one's about finishing the DLL and also something about Java interface. Make sure you go over that. And the new makeup lecture, you also want to make sure you do that. So it's rather good to do that now and get ready for written test too. You don't want to cram everything together for your final exam. I forgot exactly when your exam day is. I think it's a little bit late, April 20 something, all right? 24th? Okay, yeah, something like that, okay. So what I think something I can do for you, I can put out some survey, maybe closer to the end of the semester. I can survey the dates which you guys prefer to have some review session. We can hold it in person, bring your question here, and then we can answer. I might just be able to give you some example question as well, but I'll do my best to help you. We can even hold maybe one or two, even two review sessions, depending on how much you need. Right, we'll talk about it later. Okay, so today, my plan, I definitely want to finish the Queue ADT very quickly. We just discussed on one interesting exercise to do to help you, and do a little bit of recap before that. And then we're going to start with a brand new topic, tree. All right, get there. So this is where we were last week. So we basically talk about the Queue ADT, and that's implemented as a Queue interface, like how we did it for Stack, right? Quick recap before we move on to some new stuff. And then the only implementation that we talked about last time was array queue. As far as the assessment for this course is concerned, you only have to worry about array queue and also link queue, which I'm going to speak about very briefly today. There is something called circular array queue. That's only optional for you to study if you want to broaden your knowledge about circular array, but it's not going to be covered in any of the assessment, right? Okay, so let's now switch a little bit. I want to just draw your attention to. I was doing that a little bit in a rush last time, but just for what it's worth, give me a moment. I just want to switch to that page, and then I can talk about it. Okay, so this is where we talked about maybe last Wednesday. Okay, so if you take a look at this array queue, right, that's something you will have to study for. Okay, so let me give you the most important highlight. Every operation for the queue, like getting the size, checking that if it is empty, getting the first element in the queue, right, and also add something to the queue, all these operations do not involve any loops, so it's going to be constant time. The only operation that's going to require linear time is a dequeue operation. Why? For our array implementation, we are treating the first element over here as the front of the queue. So if you try to in queue, for example, you're only adding some element to the end. So it's not going to be involve any loop. On the other hand, if I want to do dequeue, so that means I want to assign this slot to be null and then shift everything here to the left by one position. Whenever you want to do shift, that means it's going to cost linear time for the array. So that's the part I would like you to focus on when you actually do the study. Okay, optional for you. If you want to improve such scenario, let's say I really want to treat the front of the array as the beginning of the array as front of the queue. How can I somehow improve the performance of dequeue? The answer would be something called circular array. But this part here is optional, right? If you want to study about it, I'll leave that to you. And reach out to me if you got a question. That's basically what we did last time, right? Array queue. And I want to do very quickly another alternative implementation, which is about link queue. Okay? We did something very similar when we talk about how you can use a syncly linked list to implement the stack ADT. So we're doing something very similar right now. Let's discuss them very quickly. So the way you implement this in Java is you have the queue interface, and then you're saying the link queue class implements that. And the most important attribute you have is called the list, which is of type syncly linked list, right? Similar as before. And we got two strategies. Strategy number one and strategy number two, right? You want to specifically pay attention to this line. Let me highlight it. This line over here. Okay? This line tells you for strategy number one, we are treating the first of the list to be front of the queue. So strategy number one, okay? You can think about the first of the list is the first of the queue. And for strategy number two over here, so the last element is going to be the queue, right? We kind of talk about symmetric possibilities. And for strategy number two, this part here is going to be treated as the first of the queue. Okay, so now we're clear what each strategy is supposed to do. And what we should do is to really compare these two strategies' performances and see if there's any one of them is going to dominate the other one in terms of be more efficient. Let's take a look. For both of them, if you just want to inquire about the size or whether or not it's empty, it's constant, right? Because you do have the size attributes in the singly linked list class. And to really get either the first or the last, to get the first or get the last, you do have the head and tail, right? That's not an issue. So you do have the head over here, and also you have the tail over here as well, the reference. So both of them is going to be big O of 1. Oh, let me use green, just to say it's a green lights for you. Okay, it's going to be big O of 1 for both of them. All right, let's now talk about InQ and DQ. All right. If I want to do InQ for the first strategy, right? That means if this is front of the queue, I should add something to the end of the queue, right? So that means what I should do is, let's say for InQ over here, if I create some new node over here, what I should do is, rather than this being the last, I'm going to make this one to be the last, right? And then this one here is pointing to null, right? And of course, this will be the new tail. That will simply correspond to what we are very familiar with, which is at last. And we know that it's constant time. All right? Hopefully, it's not too fast for you. It's also a very nice review about how things work. But you will definitely need that for the written test too. Okay, let's move on. And what about the second strategy? This will be the front of the queue. Now, if I want to do InQ, I'm going to go for the other end. That means I'm going to add the new elements to over here. So this is the front of the queue. This will be the end of the queue. So what I should do is I'm going to, again, create a new node over here. Okay? And what used to be the head should now be the second elements, right? And this new node should really point to over here. And that means this is the new head. Right? You can see this kind of symmetric. So that will just correspond to the at first method. And that's also constant time, right? Okay, so far so good. What we want to really understand is about DQ. Okay, for DQ, what about strategy number 1? If you want to do DQ, you want to remove the front of the queue. That means you want to remove the first. We know very well, remove first is constant time, right? So that would be constant time. On the other hand, for singly linked list, for strategy number 2, if I want to do the DQ, that means I want to remove this guy here, which is the last of the singly linked list. That one there, remember, linear time. Okay, just remember. Okay, so that's why you can see the remove last. And I can almost guarantee you will be somehow asked directly or indirectly about what's the running time for remove last for singly linked list versus doubly linked list in the written test too, right? Just make sure you can get that question right. And big O of n. Right? Apparently everything's straightforward except that this one here, you have to pay attention to it. Just don't get it wrong. All right? And of course, the obvious exercise for you, I'm going to put it down and do try it out. Okay? I want you to think about another 2 alternative strategy. Number 1, using a doubly linked list. And the first is the front of the queue. Okay, number 1. Number 2, still consider a doubly linked list to implement the queue. But now the last of the list is the front of the queue, right? Think about what's going to change in the running time. You can simply write on your notes some table like this and figure out exactly what should be the method of the doubly linked list to implement and what should be the corresponding running time. All right? All right, guys, any question until now? Good. All right, let's move on a little bit. And we just need a few more pages about Queue, and then we can do some exercise, and we'll take a short break. Okay. And this part over here is just about how we can manipulate the methods for the queue. This part here is very similar. So I would suggest this part here, I don't need to bother you too much. We in-queue Alan, Mark, and Tom, right? If you try that, I'll just do something very quickly. So in-queue Alan, followed by Mark, followed by Tom. And if you try to, if you actually try to do, I don't have any DQ here, but anyway. So after that, Q.size is going to be 3 because I got 1, 2, 3. And definitely it is not empty. And what will be the first of the queue is going to be Alan. Okay? But I think this page here is, again, to really talk to you about the idea of polymorphism and dynamic binding. Okay? That's something we discussed very extensively back in the stack case. I would suggest review that part and take a look at here. It's a similar idea. But I'll just highlight to you. Think about this assignment over here and this assignment over here. Given the static type Q over here, we can have either array Q or link Q, right? Being able to do such assignment is called polymorphism, okay? So this part here and this part over here is called polymorphism, okay? For that part, maybe I don't need to repeat, okay? It's just the same discussion as we did in the stack case. What about dynamic binding? For example, if you look at this line over here and this line over here, these two lines are exactly identical. However, they are going to invoke different versions of the in-queue because at the point that Q is called over here, its dynamic type is array Q. At the point you make this method call, the dynamic object is link Q, right? So this in-queue is going to call the version that's in array Q. This in-queue here is going to call the version that's in link Q, right? It's different, okay? But both of them should work. So this part here is about dynamic binding, okay? Dynamic binding, right? Nothing new, right? So the way you implement stack and queue are very similar. So once you understand one very well, the other one shouldn't take too long to digest completely, okay? All right, any parts you want me to repeat? It's okay? Okay. Okay, that's good. And I also got a source code available to you. You can play with it and feel free to reuse it for your own application if you need to. Okay, the final one, okay? Let me present to you about the exercise. I'll let you guys think about it for 1 minute or so, just give you some chance, and then I'll talk about it. Okay, over here. Polymorphism, dynamic binding. Okay, good. So the exercise we want to do is we want to see how we can implement a queue using 2 stacks. What does it really mean? You want to take a look at this declaration here. Okay. Yeah, sorry, I don't have any iPad page for this fragment of code. Let's take a look. Make it bigger for you. Take a look at this Java declaration here. We're still trying to implement a queue interface, but rather than using a single array or a single singly linked list or a single doubly linked list, instead we try to use 2 stacks. You can see this is stack number 1, stack number 2. Somehow this can be done, which means as far as the external user is concerned, they're manipulating a queue. But internally, you have to make it work by using 2 stacks. Okay? One stack is called in stack. The other one is called out stack. Okay? And just to help you guys a little bit, you can feel free to think. I'll give you 1 minute. Take a look at the notes over here, and then take a look at the declaration. Think about it just for 1 minute. And then I will do one example with you. And that should be rather clear. Yeah, take 1 minute. Okay, another 30 seconds, you know. Okay, just one more moment, and then we'll do one example just to make sure you completely understand how it works. Alrighty, so hopefully at least you know what the exercise is about. Okay, let's take a look. Just one example. Okay, so you can, let me try to present this way. Hopefully that will help you the most. Let's now think about this fragment of code. We have a queue object. Let's say we have already created that. And we want to do some in queue, and then we want to do some dequeue as well, let's say. Okay? Let's say from the external user point of view, how does it work? Let's understand that first. And then we'll see how that works internally. Okay? So what I will do is I'm going to use the green over here. So for this one here, let's say before that we have already created an object of type queue. Right? For that one, I assume you know how to do it. You can check out the code that we discussed earlier. Right? It's a queue. First of all, in queue Alan. Just to save my writing, I'll just wouldn't put a quote. Just say Alan. And then the second one in queue Mark. The third one in queue Tom. All right, pretty straightforward. And then what we want to do is we want to have another variable called front. Okay? And then the front is going to be, number one, is going to be queue.dequeue. All right? Which one should it remove? Apparently, this one here, right? So that means the front is first of all going to point to Alan at the same time. Remember, dequeue is actually going to remove the front, at the same time return that to whatever variable you're trying to store, right? So front at the moment is pointing to Alan. Let me call this number one. Okay? What about another dequeue? Let's call this number two. That one there is going to remove the mark over here. That's the current front. At the same time, it's going to let front, rather than pointing to Alan, is going to point to just Mark. Okay? That one is number two. What about number three? For number three here, it's actually going to, again, remove the front over here. At the same time, front is going to capture that removed front, which will be Tom. So this will be from the user's point of view. And the way to achieve this queue operation, you can use a singly linked list, you can use a doubly linked list, you can use an array, or you can use two stacks internally. That's something we'd like to find out exactly how. Okay? Good. Hopefully, so far, so good. Let's now try to think about these operations for the second round, but I'm going to use the two stacks to show to you how things go internally. Okay? I'll use a different color. Let's say for this line. And if I say I want to in-queue Alan, I will simply push whatever I want to in-queue into the stack. Okay? Alan. And then if I want to in-queue another element Mark, I'll just push onto the in-stack Mark. If I want to in-queue again Tom, I'm going to push on top. So far, I have no demand from the user to really do any dequeue or to look at the front, so I'm okay. All right? One thing to note right away. Apparently, Alan over here is the front of the queue. Make sure you know what I mean over here. Apparently, you can see Alan is corresponding to this Alan over here. Mark is Mark. Tom is Tom, but the order is reversed. So if you want to do dequeue over here, you simply just cannot get the top. You just cannot. All right? What should you do? Remember, yeah, I'm pretty sure know what you know. Remember when we did the reverse of an array, we have to somehow push everything from the array into a stack and then pop everything off. That's the insight you want to have. All right? So now, as soon as you actually got some dequeue operation, in which case you have to know where the top is. Sorry, where the front of the queue is. In that case, when a dequeue, how about this? When the first DQ is demanded. And the current out stack is empty. Okay, I'll rephrase a little bit if you don't mind. Okay, it doesn't need to be the first. There are two things over here. Number one, if a DQ is demanded, number one, and out stack is currently empty. Okay, so this is some condition you will have to encode in your Java. I'll leave that part to you. Okay, two conditions over here. Number one, DQ is demanded. Number two, the out stack is currently empty. That means we cannot access anything from there. This stack over here is supposed to restore to store the reverse order of the queue somehow. Okay, how do we do that? Apparently, we are now satisfying this condition over here because we want to do a DQ, and at the same time, our stack is actually empty. So what do? We're going to do what we did earlier for reversing an array. Pop everything off, push that here. Pop everything off, push that here. Pop this and push that. That's what you're going to do. Okay? Let's try. So we're going to pop this off. Tom is going to be pushed over here. Pop this off and push. Pop this off, and then we got Alan. Right? Do that first. You only do that when the out stack was empty. You don't really have to always popping off everything from the in stack. You don't really have to, right? That's some key. So when you actually do the exercise, which I suggested on the slide, to really implement this Java code, you have to think a little bit more carefully about some boundary cases, right? That'll be some nice exercise for you. What I'm talking about over here is a general case, which will deal with maybe about 90% of the coverage, right? So once we have done this preparation job, so now if we want to do DQ, what should we do? Well, you don't worry about in stack anymore. You worry about what's the top over here, which is Alan. So now think about this DQ over here is number one, okay? And then you're going, and also we got front. Pop this off, and then the front is going to point to just Alan. Okay? When we go to the second DQ, pop this off, and then that one there is actually going to give you Mark. Okay? When we go to the third DQ over here, pop this off, and that one there is going to give you Tom. And are we achieving correctness? Indeed. Because here we got Alan, Mark, and Tom. Alan, Mark, and Tom. So it's a correct order. Okay? This, I heard, used to be some very popular interview question, very standard one. But everyone knows about it. I'm not too sure how popular it is these days. Right? How you can implement a queue using two stacks. Right? Excuse me. Question? Mm-hmm. Yes, that's correct. That's correct. So that's why you have to use two stacks over here. If you only use one, if you only use one over here and all just retrieve by top, top, and top, you're going to get a reverse order, which is going to be very confusing to the external user. From the external user point of view, they don't know anything about the stacks that's internal. They only know about manipulating a queue. Okay. All right, guys. Any question? Mm-hmm. Good. Very good question. Yep. Let's clarify this. Okay, and then I'm going to just copy this. So let's talk about it again. The question was, what if, let's say, after the first DQ, we got another in queue, let's say, okay? Still, the same principle will apply. You only try to pop everything off on the in stack if you got these two conditions satisfied, all right? But let me write it down. It's a very good question. I'm glad you asked. So let me modify the code very slightly. Can we say after the first DQ, can we just add one more line? Let's say queue dot in queue. Let's say Jin. That's what you were asking, right? Okay, very good. Let's try. And let me write down the condition again. Only pop everything off in stack and push to out stack. You only do this if two conditions. Number one, A, front, which is one of the accessor method, right? That's pretty much like a pop. Pretty much like a DQ. Front or DQ is demanded. Demanded. And number two, the out stack is currently empty. If it is not empty, you don't need to worry. Okay, so these two conditions are like a repetition from before, but let me emphasize they are so important. All right, let's try. So let's try this. Alan, oh, sorry, I somehow missed the label. Okay, otherwise it could be confusing to you when you look at the notes. There we go. Okay, Alan should be pushed onto the in stack. Mark should be pushed over here. Also, Tom should be pushed over here as well. Okay, and then we're going to do DQ. Let's say the first one. That one there is going to be, well, that one there we are demanding some DQ, right? Satisfying condition one. Condition two is also satisfied because this is empty. Okay, so we're going to do some preparation. So we're going to, first of all, pop this off, Tom, and push. Pop this off and push, Mark. Pop this off and then Alan. All right. And then for this first DQ, we can simply just pop this off, right? So the first DQ is going to point to just Alan. Okay, that's number one. And then we got another in queue over here. In queue, no brainer. All you do is push to the in stack, no brainer. All right. So all you do is you just push this into Jim. This might seem a little bit confusing at the moment, but it's not really. Okay. Think about what's happening here. The queue used to be Alan and then Mark and then Tom. You're basically pushing Jim to be here, so it's all the way to the end of the queue. You don't really need that until the out stack has been exhausted for all the DQ. All right. All right. After this, what should we do? What we do is we're going to talk about another DQ, number two. So we're going to remove this Mark, and then it's going to be Mark. Number two, and then number three. We're going to pop off Tom, number three. And it's going to be Tom. All right, so far so good. And now question. What if I got another DQ, right? That should be a follow-up to your question, right? Let's say I want to say, oh, let me use a different color. Q.DQ. Now, what's happening here? At this point, we are demanding a DQ, satisfying condition one. And the out stack is completely empty, satisfying condition two. So what do? Pop off everything and push here. All right? So what's going to happen is we're going to get, sorry, I'm running out of space, but you can imagine you're going to get this pop off. So Jim is now going to be the top of the stack. And then when you do number four, DQ, the front is now going to point to Jim. And then you're going to remove it from the stack. All right? What you really want to convince yourself is like this. From the external user point of view, how should a queue work? Get it straight first. And then think about how the two stacks are going to operate to be consistent with how a queue works. All right? No, you don't have to. Because when we actually, you mean DQ, wait, where? So which part? No. You do, first of all, when you say in Q gym, right? When you say DQ, you don't pass any value over here. You cannot say DQ gym. You cannot say that. DQ doesn't take anything, right? So think about this. When I say in Q gym, I'm adding gym to the end of the queue. And then if I do some DQ right away, it's not going to impact this element here because remember it's first come, first serve. I'm still going to impact just the beginning. So that's why at the moment, if out stack is not empty, I can still use it until it's exhausted. That's the very important insight to really look into. Okay? Right, again, so you really want to make sure, understand about the last in, first out versus first in, first out. Okay? These are the critical principles you want to remember to really be creative about designing other algorithm. Okay, I'm really glad you actually asked that question. I think that really made the discussion complete. Good. Go ahead. Yeah, you can say that. Yeah, the observation was, so our stack's main purpose is to be reserved for the front, like a front inquiry, the DQ. Yes, that's correct.
Yeah, in this case, since we are moving out the only thing that's actually satisfies that.
Yeah, of course. Yes. Alrighty. So guys, let me take about 1 or 2 minutes. I want to wrap up this lecture here, and then we'll take a short break, take attendance, and then we can start with a new lecture. All right, bear with me, and then you guys can take a short break. So now we are done with everything I want to say about the stacks and queue. We have done quite many examples and illustration. Make sure you review them. They are very fundamental ideas for you to know, right? And I want to just give you 1 minute, very quick high-level overview about the optional material. Again, they are not going to be covered in any of the assessment, but I do encourage you to really try to study them. It's very good for your knowledge about this course. Okay. All right. You can find about these 3 main topics. Okay. One is about a little bit more about modularity, design by contract. It's going to strengthen your understanding more about ADT. Right. So that part you can just find where the lectures are. Okay. The second part is about circular array. So this is how we can improve the performance for like a DQ when you actually use use a DQ when you actually try to use an array implementation. And the third one here is about if currently we got fixed size array when you try to implement the stack or queue. What if I want to say dynamically, whenever a user has filled up the array, I want to resize the array automatically. Then there are 2 strategies over here for you to think about. One is called increments. The other one is called doubling. And for your information, in the Java API library array list, they use the doubling strategy for a reason. Because asymptotically, the doubling strategy is more efficient, but only in the amortized sense. That's something I also discussed in detail in this optional lecture over here. Right? So when you go over the slides over here, you can definitely take a look. Right? So, and on the other hand, I'll just show you one more thing. Okay? Especially, I really encourage you to go over the amortized analysis. Okay? So the notes is actually over here. I'll show to you what kind of analysis you can expect to learn about. Okay, so just give me 1 moment. I'm going to search for that lecture very quick. Stacks and queue. I believe, yeah, this one here. Yeah, when you study that lecture here for the amortized analysis, you will see that something like here. That's for circular array. You're going to use the percentage sign like a modular operation. Okay, and then, okay, so this is the part about dynamic array, either increments or doubling. It turns out doubling is the winner in the amortized sense. Like you have to use an average case analysis. Well, I really walk you through about all the math about how things can be done, right? Pretty heavy in terms of math, but the conclusion is if you try to do just fixed increment, amortized analysis will give you like a constant time, all right? And if you try strategy, amortizedly speaking, is going to give you constant time. You have to do some heavy math over there, all right? Hopefully, some of you will actually try to explore this lecture here. It's very good for your knowledge. All right, that's everything I would like to say about this lecture here. And just make sure you catch up with the study if you haven't, and then get ready for written test number 2. Okay? Okay, why don't we take a short break and take attendance, and then after that, we go for a new lecture. Okay, just get your device ready, and then I'm going to start the iClicker right away. Okay, the poll. There we go. Select. Okay, check in, please. Yeah, we are now taking attendance. Just get your device ready and check in before I close it. Okay, everybody's good? Okay. Okay, I'm just about to close it. Okay. Okay, can I? All right. All right, thank you. So take a 2 minutes break, and then we'll come back for the new lecture. Yeah, 2 minutes. All right, 1 minute, and we'll resume. Okay, just 1 moment, and then we'll get started. Alrighty, let's get started again. Okay, we got about definitely less than 40 minutes, but we'll see what we can do today. Today is going to be some very gentle introduction to this very big lecture series. Let me give you guys some roadmap about what I plan to cover. Okay, so this will be in some way the only big topic that we have to finish off for this semester over here, but that one has many parts. So we're going to talk about the general concept about trees, which is also a very popular interview topic. So when we actually design your programming test number 2, we also try to get you prepared for that kind of a programming interview to give you a feel. So for the trees, there are several parts that we need to talk about. Number 1, general trees. And number 2, binary tree, which is a special kind of general tree. Yeah, we call BTs sometimes. And then the next one will be binary search trees. And BSTs. The next one, we're going to talk about balanced binary search trees. Okay, and then after that, we're going to talk about another ADT called priority queue. And the final one is something called heap sort. So these are the main topics I would like to cover before we end the semester. And this part over here will be part A, which I hope to finish in hopefully 2 or 2.5 classes. And the next one will be about binary search tree. That'll be part B. And then this part here will be part C. And hopefully we can spend relatively more time on this part over here. That part is going to be a little bit tricky and math heavy. Okay. Right, so that'll be the plan by the end of the semester. Okay. Alrighty, let's now have some gentle introduction today. Okay. So learning outcomes. We're going to talk about linear versus nonlinear data structure. So far, all you have learned is about arrays, linked list, even stack and queue. They are more like a linear data structure, not nonlinear. I did mention briefly about how you can distinguish between linear and nonlinear back in the very first class. You can feel free to take a look at your notes if you took any notes. Okay, but I'm going to repeat that points today. And some terminology about general trees mainly today. There will be some binary tree specific terminology that we're going to talk about, possibly on Monday. Okay? And then how you can implement a generic tree. The way you implement a generic linked list in Java, you're going to use something very similar for generic tree. Okay? That's what we'll see. And then we're going to look at mathematical properties of binary trees. That's also very important. When we have to argue about the asymptotic upper bounds for any of the tree algorithm, we have to use a mathematical property. That's so important. Okay? And then tree traversals, how you can really systematically go over every node in the tree. There are 3 different flavors that people like to use. Each one of them has its specifics that you have to know about. We'll get there. Not today, possibly on Monday. Okay, general trees. So let's review what a linear data structure is. What's a linear data structure? It's a sequence where stored objects can be related by predecessor and successor, right? So this is the more formal definition. Okay, let's try to look at this right away. The data structure you have seen so far in the course, right? You have seen array, you have seen doubly linked list, you have seen singly linked list, right? All these are the so-called linear data structure. Let's again emphasize why they are called linear. As long as you have the notion about in the collection, is there a unique element that will go after me and one unique element that will go before me? If the answers to both are true, in that case it's linear. Okay? So think about this. In the case of array, if I'm over here, let me use okay. Let's say I'm here for this particular elements, okay? Over here, you can see this is index 1. In that case, this index here and this index here are the unique successor and predecessor, okay? This will be the unique predecessor. And this will be the unique successor. Right? Of course, it's not just for this element. For example, for this one here, you do have another unique successor, unique. But of course, you don't have any predecessor. Right? As long as it's unique, then you're good. And apply the similar notion, let's say for singly linked list. Let's say given this node, I know that I have a unique successor. Given that the next is a single attributes in the class for me to inquire about, right? So this link over here tells me this is a unique successor. Similarly, when we talk about, let's say, doubly linked list over here, so you can take a look, for example, here, and also here, it's also unique pointers. That's also unique. Successor and predecessor. Okay? Yeah, pretty simple definition, but you have to know it. So do, well, I'm not sure it will be on your exam, but in case I ask you about what is the difference between linear versus nonlinear structures? You want to know how to answer that. All right? Okay, that's about linear. Let's make sure we understand that very properly since we have learned about so much about them. And how do we tell nonlinear? Oh, so these are just what I just mentioned to you. And a tree ADT is one example where it's nonlinear. Basically, if it's not linear, that means you have multiple ways to get to your successor, all right, or your predecessor. Oh, question. It's a good question. For hash set, I would say this wouldn't be a practical question. I tell you why. Because here we say a linear data structure, first of all, it should be a sequence. A set is not even a sequence, right? Because order is not really important. So that's a good question here. So guys, the question was, if you consider a data structure like a hash set or hash map, so you will not even discuss this because there's no ordering in that case. So it's not even a sequence, okay? Very good question. All right, what about tree ADT? All right, I'll give you some idea right away, okay? So this is a tree. I haven't introduced any terminology to you, which I will very soon. But if you look at this structure here, this categorically is very different from this or this or this. Okay, so let's say this. If I'm currently at this node over here, okay, how about temporarily? Imagine that if I have this node over here, right? If you rotate, oh, sorry. Let me do a little better. Imagine that, hopefully I can do that. If I try to rotate like this, that might appear a little bit more closely to what you can imagine. If I am this node, now if I want to get to my successor, how many possibilities do I have? Either here or here, right? Okay. Either here or over here. So that means I got multiple successors, right? But I would suggest this is not the way you should think about a tree. Let me put it back. Oh, sorry. There we go. Okay? So think about these two are multiple successors, not unique. Multiple successors. Not unique. Okay. And there will be, also we call the tree structure something called hierarchical structure. Okay. Hierarchical structure. That means there are levels. Okay. Let's see what I mean. I'll give you a little bit more formal, precise definition about levels. But for now, let's see just visually. If you try to divide the trees into level, this will be here level number 0, in which case you got only one node. Okay, this will be so-called level number 1, in which case you got 2 nodes, multiple. Okay, and then you got another level, level 2, and then you got level 3. Is it always the case that the lower the level, the more nodes you have? Not necessarily. But if you restrict our case to be balanced binary search tree, it will be the case. But let's not worry, we'll get there. A general tree, you just have to remember, number 1, each node has multiple successors. So that's why it's not linear. It should be non-linear. Number 2, you can divide your nodes into different levels. Every level may have more than 1 node. Except for the very first level, it's always just 1 node, which is called the root. Okay? All right, let's now go back to the slide to see if I missed anything. Okay, store some data objects. We're going to see exactly how we can declare some node in the tree. So think about when we implemented our singly linked list or doubly linked list, we try to declare Java class for a single node. Similarly, for the tree, we're going to declare the structure for a single node in the tree. We're going to see that, okay? Maybe today or maybe on Monday, for sure. Okay, and then the nodes, okay, different levels, and then it's a hierarchy, right? And what we're going to discuss is about the terminology for tree. Maybe back in your high school, maybe one of the activity is to form the family tree of your family, right? So all the terminology of the tree, we kind of borrow that from the family tree idea. Okay, we're going to see. This part here should be rather straightforward, but I think once we get to the later one about subtrees, and also depth and also height is a little bit trickier. So we're going to get right. Okay, let's go one by one. Okay, you can look at the slide as well, but I'll just use the iPad here. Okay, first group of terminology to clarify. Okay, number one is called the root of the tree. Over here, the single top node is called the root. I know in real life, the root of the tree should be at the bottom and the tree should really grow top. I'm sorry, for CS, it's the other way. Okay, root is always the top, always one, unique root. And the next one will be something called parent. The way to understand informally is the immediately above, the immediate node that's above you. Immediately above node. For example, if I have Ernesto over here, who is his parents? David. That one's very straightforward. I know in real life we got two parents, but in tree, only one parent. Okay? And Elsa's parent should be Quiz. Quiz's parent should be David. Okay? And one thing, okay, can you tell me the answer to the following question? Does every node in the tree have a non-null parents? Let me repeat the question. Does every node in a tree have a non-null parents? Okay? If you say no, tell me which one has a null parents. Yes, go ahead. The root, exactly. The root over here, David, has no further parents, so their parents will be null. On the other hand, if you got Ernesto, Shirley, Elsa, whoever, they always have some parents, which is not null. Okay, that's also important. So David here, the only node whose parents is null. Let me give you a little bit look ahead. So that means later on, when you try to program trees in Java, the parents being null is actually a very typical base case for recursion. Okay? Remember the base case usually for singly linked list. You have the current reference and then go all the way until current.next is null. Similar. You may start from, for example, from here. You just go parents, 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 and then, oh, the parents is null, so I should stop here. Right? That's the idea you want to keep in mind. Okay? It's a very typical base case. All right? Right? And then children. Okay? That one is kind of symmetric to the parents. For example, who will be the children for Elsa? It should be immediately below. So these are the children. Of Elsa. Okay. And I'll talk about ancestor and descendant maybe on a separate page. I've realized the diagram is getting a little bit quite occupied already, so I don't want to cause too much confusion. But siblings is easy. All the nodes sharing the same parents should be the sibling, right? That makes sense. Who will be the sibling for Shirley? Vanessa and Peter, because all of them have the same parents. Who would be the sibling for Elsa? Anna, because they share the same parents, right? Okay. So I'll just give you one example. So for sibling, by definition, it would be the nodes sharing the same parents. For example, Ernesto and Chris. All right. Okay, so far so good. And I would like to talk about ancestor and descendants, maybe on a separate page. Okay. Okay, okay, good. Okay, so let's talk about both of them. And let's see the definition from the slides. Okay, we talk about the root, we talk about the parents, we talk about the children, and that's good. And let's talk about ancestor. Okay, so what's really the definition for ancestor? If you got some node n, and then the n itself, n's parents, and n's grandparents, and etc., all the way to the root, these are called the ancestor for that particular node. Question? No node can have multiple parents, always unique. Very good question, but I'm going to write it down. Very good. So, every node has a unique parents. So this is one of the fundamental rules about being a tree. Let's say if a node is allowed to have multiple parents, in that case you got multiple predecessors. In that case, it's not a tree anymore. It's something that's even more general called a graph, which we don't cover in this course. You guys will learn much about graph in 3101 later, but not for this course. Okay? But just for your information. So unique over here is so important. Okay, let's now talk about ancestor. Again, let me remind you about the definition. So if I want to talk about n's ancestor, first of all, n itself, its parents, grandparents, all the way to the root. Okay, so for example, let's say this. Let's do two examples. Ancestors of, let's say, Shirley. First of all, calculate in your mind how many. How many ancestors? 3? Okay, it says 6. Why don't you tell me which 6? Shirley, and then? Oh, sorry. Okay, sorry. Shirley, and then? Absolutely. So it should be 4. That's perfect. Thank you. All right, so this is how you think of it. Starting from the node that you're inquiring about the ancestor, and then you basically follow through the edges, and then all the way to the root. All the nodes that's actually covered will be the ancestor. Okay, so these are the ancestor. So you got Shirley, and you got Elsa, you got Chris, and you got David. Okay, and it's also important to note this particular path, which will go from the node itself all the way to its final ancestor or the top ancestor all the way to the root, is something called ancestor path. So why is ancestor path so important? Later on, we're going to talk about some algorithm of inserting and deleting nodes from a binary search tree, in which case we have to know where the ancestor path is. We'll get there a little bit later. I want to give you some look ahead. Yes, question? Okay, the question was, I'm glad you asked. The question was, when we talk about a node's ancestor, why should we include the node itself? I know it doesn't make real sense, but for our definition for some algorithm and some mathematical property, it would be better, it would be easier if we include the node itself. Okay, yeah. Okay, you just have to remember it does include the node itself, very important. Okay, let's have the symmetric definition, which is descendants. If you go back to the slides, what about descendants? Descendants of a particular node n is going to include its children, its grandchildren, and all the way down to when you cannot reach out any further. Okay, let's see some example. How about this? For this one, let's try 2 examples. How about Ernesto? How many descendants are there for Ernesto? 0? 1, not 0. That's a common mistake. I'm glad you make it right now, right? So don't forget himself, okay? Ernesto. And something very strange you might be thinking, but I can tell you you're right. You're thinking, oh, so that means a node by default is going to be its ancestor and descendant at the same time. You're right. By our definition, that's the case. Doesn't make sense at all, but that's the definition we have to know. All right? I'll write it down over here for you. A node is both its ancestor and descendants at the same time. Okay? Yeah, it's an important definition you have to remember. All right? So here we say descendants of Ernesto is just Ernesto. That's good. How about let's try another one. What about descendants of Quiz? How many descendants of Quiz? 5? 6, right? If you said 5, maybe you forgot to count Quiz itself, right? Right? Don't forget, all right? It's going to be Quiz himself. Children, another 2. Children's children, which will be another 3. So the idea about figuring out the descendants and ancestor itself is a recursive idea. Some exercises I put on the slides is for you to figure out the method. But before that, I'll give you other examples. Just make sure you can do it. Mario. Oh, okay, good question here. Basically, you're saying that if I can somehow figure out my ancestor path, would it help me to figure out which level I am in, for example? Yes, indeed. So either today, most likely Monday, we're going to take a look at, once we know the Java basics, for declaring a tree, how you can do the various calculation. One of them is calculating the depth of your tree, of a node. In that way, yes, that will help you. Absolutely. Yes. But we'll get there. Okay, for quiz, I'm going to write it down just for completeness. It's going to be quiz, Elsa, Anna, Shirley, Vanessa, and also Peter. Okay? And of course, and finally, which is also very important, what about the descendants of David? Remember, David is a special node. Who's the root? Who will be the descendants of the root? Everything in the tree, including the root itself. Okay? So, the way I would like to write this one is an insight. Okay? Descendants of the root cover the entire tree. Okay, entire. Yeah, sorry, that one is not written very properly. All right, that's another insight you want to know. All right. All right, that's about ancestor versus descendants. Okay, next one. Subtree. Okay. So now we are getting a little bit more into thinking about tree recursively. So subtree is a very fundamental concept. Okay. Let's now take a look at some definition on the slides and see how we can visualize it. Okay. all the nodes with the same parent. Okay, that's sibling. Okay, that's fine. We talked about it already. Okay, I want to get to the subtree. Okay, sorry, over here. There we go. Okay, the tree formed by descendants of n is called a subtree rooted at n, right? So I'm talking about this bullet point here. Let me read it again together with you. The tree formed by the descendants of n is called a subtree that's rooted at n. What does that mean? Okay, it's really important. Okay, for example, if I want you to identify for me, for example, the subtree rooted at David, well, it's going to be the entire tree. That is the largest subtree you can ever get because it's rooted at the actual root. Okay? So the way to draw to visualize it is something like this. Okay? Let me erase this color over here. And then think about this here is a subtree. Okay, cover everything. Okay? The absolute root. Right, the entire tree. Let's try another one. What about let me give you the minimum possible. Rooted at, let's say, Peter. Well, by definition, it's going to be all the descendants. Okay? And how do we draw that? Peter. This is a tree. Right? So this is the subtree rooted at Peter. Okay, hopefully getting us a better feel, right? Let's do something that's in between. Okay? What about subtree rooted at Elsa? How many nodes are in that particular subtree? 4? Agree? Good. Okay. This will be the root, and the subtree is going to be this part over here. Okay, how about this? All right, so that's the subtree, which is going to consist of Elsa and all the descendants. And then I'm going to give you some question here. Subtree rooted at Elsa. All right, so here is now a very important question. How many subtrees? Are there in the tree? Yeah, when I say the tree, I mean talk about this one here. Right? I already gave you some examples. Now I'm asking how many in total? What you want to think about is how many roots that can possibly be the root of the subtree. Right? Yeah, it will be the same number. It will be the same as the number of nodes in that actually tree, right? Because this can be the root of some subtree. This can be the root of some subtree. This can also be the root. This can be the root. Everything. That will simply just be the number of nodes in the tree. Of course, each subtree may have different size. Okay. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Number of nodes in the tree. Okay, I have some exercise for you, and then I can move on. I have a table over here. Okay, so this This will be the size of the subtree. And this will be the actual subtree. Okay? And then I want you to enumerate size 1. And then size 2. All the way to, what's the maximum size of the subtree? Well, the 8, right? The entire tree, right? All the way to 8 over here. And then for each entry over here, I would like you to identify where exactly. Okay? So now, just for this one here, how many subtrees are there that are of size 1? How many? I heard 3. Any other answer? Huh? 8? For example, this subtree over here is definitely not of size 1, right? This subtree over here is of size 1, 2, 3, 4. So here I'm asking how many subtrees, first of all, are of size 1? Tell me which 5. Ernesto? Yep. Anna? Yeah, exactly. So these are the 5 subtree roots where the subtree has only size 1, 5. All right? So you got 5 subtrees. And it's going to be the Anna, Ernesto, Shirley, Vanessa, and also Peter. Right? So these are all the 5. Right? You do the similar exercise to figure out how many subtrees are there of size 2. Right? In the test, I might say, tell me how many there are for subtrees of size something. Right? Okay, hopefully you got my idea about doing this exercise. Okay, 3 minutes. Okay, why don't we talk about one more thing? Okay, external node, internal, that's it. Okay, and then we'll continue on Monday. Okay. External node, internal node is actually very simple idea, but they are also very important. Okay. Okay, we'll talk about, okay, so here, the nodes with no children is called external nodes or leaves. Okay, right away. How many external nodes do we have that has no children? Vanessa, Peter, Shirley, Anna, and Ernesto. Agree? So these are called the leaves. Peter, Anna, Vanessa, Shirley, and Ernesto. So these are the external nodes. Oh, sorry. Yeah, remember I spoke to you before about the root being some very typical base case. So are the external nodes. When you try to program recursion on tree, if the base case is not exactly just root, another possibility might be the external nodes. Okay? Base case of recursion on the tree. Right? Symmetrically, any node that has at least one child is called internal nodes. They don't overlap. So David over here definitely has at least one child, Chris, and also Elsa. So these are the internal nodes. And they are usually the recursive case for recursion on trees. Oh, give me a moment. Let me write it down, and I'll take a question. Internal nodes. So these are typically the recursive cases of recursion on trees. Yeah, question. Go ahead. Yeah.
Is there a similar term for?
Oh, well, to be honest with you, I don't think so. Yeah, maybe branches. That might make sense, but no. So yeah, so whenever I talk about either external nodes or leaf, I'm really talking about these kind, and then internal nodes. All right, guys, what should you do before Monday? I'll give you one little extra work if you're willing to do it, okay? I would suggest go back to the slides and then, of course, review what we have got so far. And then I would suggest take a look at this particular slide, just this one here, okay? Take a look at slide number Okay, look at slide number 14. Okay, I want you to take a look at a particular slide. That one tells you the template that you will be given for the assignment number 3 and also for your programming test number 2. Take a look at that, and then we're going to go over some example on Monday. All right, thank you so much. I'll see you later.